started. Welcome to the 2024 SUS State of the Union meeting. So I've done lots of hard work, and I'm here to present, well, the progress on the compiler. So last time I explained to you all of the motivation why I'm designing SUS, what makes SUS a good choice and everything. I've got like 25 slides dunking in all of the competition, but I'll keep it short here. The main purpose of SUS is that you, the programmer, are in the driving seat. That means you have to design your hardware, you're responsible for every component of it, but that also gives you enormous power to make sure that the hardware works and builds exactly the way you want. SUS only provides, I should enlarge this a little bit, 1 second, because my presenter view is too small, because it keeps getting smaller. Right. So we only provide tools to deal with complexity in SUS, not to abstract it away. So you can still build any hardware you want, but just make the intrinsic complexities of hardware easier to deal with. SUS is basically like a direct translation to the netlist that you're getting out at the end that you can then feed into, say, Vivado or Quartus, and then you can get direct feedback from the synthesis tool to see where you can improve your hardware, where routing conflicts are cropping up, and how you can actually fix them. And finally, SUS is there to provide some immediate in-editor feedback to tell you what you're doing wrong. If you're building like bad feedback loops or something, then the compiler will tell you and will hopefully guide you reasonably well towards improving your code so that it does work. One of the ways in which it does this is, for example, here. So we've got a little screenshot of some SUS code here, and it has helpfully annotated this pipeline register. Because what we're doing here is we have instantiated a state register, we've initialized it, and now we have built a feedback loop, but this feedback loop has an extra pipeline register within it. I'll get into the details of how that works later. But in this case, the compiler has popped up a helpful warning message to tell you, hey, this is part of a net positive latency cycle, so get rid of that latency register or rework your hardware. That was all of the motivation. So now I'll go into the language, and I'll do this through examples. So SUS is a direct pretty much translation to netlists. So here we've got a little module that implements an XOR gate. Of course, these are in the language itself, but just as an illustration. We've got two inputs here, x1 and x2, and we've got an output there, y, and then in the middle, we have got a few intermediary operators and variables that compute some values in the middle. And then at the end, we assign to y as our output. Here, down below, you can see how you would instantiate such a module. So you can just kind of use it in a function call like syntax. And that synthesizes to these gates over there. Then you have conditions. And these are pretty common in hardware design that you want to have multiplexers. So one important thing to know about hardware design is, of course, all hardware is always running. Like you can't just conditionally run some hardware or turn some hardware off. Every bit of hardware on that chip is running all the time. The only thing that differs with conditions is if assignments actually get assigned. So in this case, this synthesizes to this, where we've got our inputs A, and then we've got to check if it's less than 0, and if it's less than 0, it checks or it uses the output of the negate block, otherwise it uses the value itself. But if you have more hardware in the middle there, then that hardware is, of course, still being executed. Now, these are runtime if statements. You've also got generative if statements, but we'll get to those later. Now, hardware design is different from software design in that all hardware blocks are basically little bundles of state that you can poke and that you can get poked by in return. So, for example, we've got a module here that implements a for loop, a runtime iterator, and it's got two interfaces. It's got what I call, the internet's down, oh well. It's got what I call a start interface, which like sets the iterator going. You give it some value to run up to, and then once you've started that, it has a trigger interface, which is kind of like a callback within hardware that then triggers your hardware to tell it, OK, here's the values that I'm iterating through. And that down there is basically how it's implemented with a condition and such. So how would you use it? Here's like a little wrapper. We get in an array of some values. We have an output for output values. And then we instantiate our iterator. And then we can tell it to start iterating at some point. And then we can tell it to, or we can use the callback iter there like that. Now, I have in comments some future syntax there. I call these conditional pass-through and conditional bindings. And these will make it much nicer to work with actions and triggers as I've defined them above. But this is future work. Right now, you have to use them in the old Verilog style of module instantiation. And the Zoom meeting is back, so I'll quickly share my screen again. Zoom. I'm so happy everything's going to plan. Get it. Can you give me a quick sign if you're seeing me or hearing me? OK, perfect. Yeah, you didn't miss much. It was not very interesting. So then we have generative code. With generative code, hardware is often very repetitive. And so we want to have some kind of metaprogramming ability to generate large portions of hardware so that we can do things in parallel. So as opposed to HLS or anything you're used to, these for loops are not being converted to any kind of runtime pipeline with scheduling and blah, blah, blah. This is just generating 600 multiplier blocks, and then like all of the adders needed to put everything together. It's straightforward. There is only one obvious hardware instantiation for this module, and that is always the case with SUS. Now, SUS operates on two levels. So you've got the metaprogramming language here, which are these for loops, and it generates the runtime statements in the middle. This is something you have to get used to. Yeah. Now, we've got generative code within the module, so we can do for loops, we can do variables, we can do conditional, ifs, et cetera, et cetera. But of course, very often you want to be able to have generative code that transcends to submodules. And for that, we have templates. So here, for example, we have a little template that does the slice of an array. Up top, we have our type parameters. So this takes any array of any type T. T can be int, bool, mystruct array of 20. And then you have value parameters. They're part of the body of the module. And this is because like maybe you want to assign some default values. Maybe you only conditionally want to take some value parameters, etc. How you then instantiate this template is like this. So this is kind of a syntax borrowed from Rust with the double colon there. You put in all of your value parameters first, and then you put in your type parameter or your type parameters, how many you have at the end. And this is how you then instantiate them. The intention in the future is to have inference on these parameters as well. But we're not there yet. But it is one of the high priority items on my agenda. And once we have templates, we can do recursive modules. Lots of hardware structures are trees, so recursive modules are really quite important. Here, we've got a module tree add. It takes in a whole bunch of numbers, and then it compresses them all down to one sum of them. So we've got a base case, or we've got two base cases, the case where there's 0 elements and the case where there's 1 element, and we explicitly handle those. And then we have the recursive cases. So basically, we split our array into 2 chunks, and then we add up, or we tree add each chunk individually, and then we can add up these results as well. And at the end, if we want, we can add a pipelining stage to that as well, because the compiler can just add them there, and there's no issue with that. Like, this is kind of part of the philosophy of SUS that it's really, really easy to add pipelining stages anywhere. If you add pipelining stages somewhere, they won't break the code They might break your build, but then you have to fix the issues that the sys compiler found in your code. One final example to illustrate how the generative code works is FizzBuzz, the all too popular interview question. Basically, the question is you get some number and you have to say if it's divisible by 3, you output fizz. If it's divisible by 5, you output buzz. By both, you output FizzBuzz, and otherwise you output the number itself. And here is the sys code implementation of that. I had to use numbers because, well, I don't really have strings, but the principle is the same. But of course, if you actually want to synthesize this, well, many hardware platforms, they don't have modulo blocks, or they don't have dividers. So we can actually generate a lookup table for it, also at compile time. So here, at the top, we say how big is our lookup table. And then instead of having our code be at runtime, we've added gen in front of our variables. And now this for loop is executed at well, the for loop was always executed at compile time, but if statements are executed at compile time. And basically, this whole block here is computing the values for this lookup table. And the only runtime statement at the end is this fb is lut of v, where we index into the lookup table to get our value. And the fun thing is, because the sys compiler is so tightly integrated with the IDE tool, you can actually hover over variables and see what the compiler generated for this lookup table, which is really nice to have some feedback while editing your code. And you can, you can look at the other ones, but I found this one very surprising, actually. So that's why I show it. Then another thing that an astute programming language designer among you may have noticed is this here. Take a moment to think, what could be the issue with these two statements here? Like, from a programming language design perspective, what would make this really rather difficult? What we are doing here is we have a variable up there, an integer, and then we're using that variable within the type of another variable. Now, functional programming people will tell you that this is a very bad no-no. This is called dependent types. And asking ChatGPT tells me that dependent types are not quite fun to work with. Now, I must admit, dependent types are quite fun if you're really into typing, aka if you are working for some functional programming department, because then you can get several PhDs out of it. But I only have time for one PhD, so I need to find a hacky workaround to get around it. This brings us to typing in the sys compiler. Typing is done on 2 levels. So this statement up there, the problematic one, is typed in 2 stages. First, we do abstract typing, where basically we strip out any of these variables within the type. So our gen int of table size just becomes int array. We do this so that we can already do some basic type checking without getting rid of all of the templates. And then we can also have like LSP information. So for example, if we have some module, then we do my module dot, and then it can tell us what functions or what ports are available on this module. And that is based on this abstract type. Also, perhaps in the future, we can use it for things like trait bounds. So say you have some trait to say addable, and then you can implement that trait for integers or for floats or for vectors, etc. On the other hand, once we actually instantiate our module, we fill in our types, we fill in all of our values, we get concrete types. And so here we have int of 256, and now we do another round of type checking on the instantiated module, where we check, okay, are these arrays actually the same size so that we can assign them, etc. These concrete types are then actually used to define the wires in the hardware itself. And this way, we've sidestepped the whole issue of dependent types, because the variables actually never appear within the types. How you can see this in the compiler is, again, if you hover over some value. So here we have our 3add module again. If you hover over this values thing, At the top, it'll tell you the abstract type. It is an input int array values. And then, because it's a recursive module, we've instantiated originally with size 255. Then it's split it up, split it up, split it up. And so these are the concrete types of all of the instantiations of this module. So we've got 1, 255, then 127, 63, etc. And you can see that also in the UI. Maybe one thing that you might have noticed here is, what is this quote 0 here? I've gotten quite some complaints from people, like that is some ugly Rust-style syntax, but it has a purpose. And this purpose is for latency counting. Latency counting is SUS's approach to pipelining. Basically, the philosophy of SUS is, as a designer, you will only ever be using 2 types of registers. You either have state registers, which really take part in the core functioning of the design. So like a state register might be some accumulator or something. These are registers you can't do without. On the other hand, there are registers that crop up because your tool complained to you that your timing was not being met. And these you add are latency registers. They are registers purely there to shorten the critical paths between components. SUS treats them separately, both for clarity in the code and because it handles latency registers in a slightly different way. Just as an example, here's a little module that implements the Fibonacci sequence. So we have got our current value, we've got our previous value. From these, we compute our next value, and then we shift them through. These are state registers because they are critical for the proper functioning of the design. On the other hand, let's say we want to do a module that raises some value to the 17th power, chosen for convenience of the example. So we have a whole bunch of multipliers that we have to put back to back to reach the 17th power. And we have noticed the critical path between I and O was a bit too long. Our clock is too slow. We want to speed it up. So we have decided to add a few latency registers. Doing this is as simple as just adding the reg keyword on a few statements, and this adds the latency registers in between them. The compiler will then see that there is a parallel branch and add extra latency registers there to compensate for the delay, such that everything stays in sync and all computations still happen on related data. What it uses for this is the latency counting process. So we have our 0 over there and our 2 on the other side. This is a value stored per wire, which tells the compiler how much offset it is. So like if one variable has an absolute latency of 0 and another has absolute latency of 2, then the compiler has to instantiate 2 latency registers somewhere between them. We can extend this. So in SUS, you have the full freedom to have your ports come in and out at any latency you want. This is opposed to many other languages, or many other automatic pipelining approaches, which tell you, OK, just give us some combinatorial block of hardware, and we'll add, say, 10 pipelining registers across it. But that requires all of your inputs and outputs to be synchronized to these 10. But SUS gives you more freedom, because in my experience, modules tend to have unbalanced latency registers around their inputs. So in this case, we've got a few factors that come in at cycle 0. 2 cycles later, we want to get some extra additional data. We produce a product at cycle 2, and then 1 cycle later again, we produce a total. And the compiler can infer the absolute latency of all of these ports, so we don't actually need to write it on the signature itself. It will infer them itself. Sometimes it is necessary to explicitly specify them, because there are some undecidable or, well, unambiguous cases where the compiler could assign multiple ways for the ports to be. And in that case, the compiler rejects it and says, OK, annotate the latencies yourself. But these cases are very rare. And actually, yeah, you need to really do it on purpose to get the compiler to complain about that. But to illustrate it, I've got a module here that has explicit absolute latency of 0 and 5 here, and that forces the compiler to instantiate 5 latency registers in the middle there. Now, not everything is a nice combinatorial feed-forward pipeline. Often you have more complicated blocks, like, for example, a FIFO here. And the observation here is that the latency counting idea doesn't fully translate. Because while some ready signal on the push side of your FIFO might be very highly related to the valid data and data in signals on the push side, this ready signal is not really related to the request signal on the other side. Like, there's no one-to-one match there. And with latency counting, we really want to associate a bunch of data together that like kind of travels together through the pipeline. So what we have is we have multiple domains for this FIFO. This FIFO has a push domain, where all of the signals are related, and a pop domain, where all of the signals are related. And so in this case, it's a FIFO that leaves 3 cycles of pipelining slack for the input side, and then it itself takes 2 cycles to produce data if data is requested from it. Internally, in this FIFO, of course, this barrier between the domains will also occur. And so here, I've neatly displayed how it would look. So we've got in our FIFO a write address, a read address register. These are on opposite sides of the latency boundary. In the middle, it's using a big memory block to store all of the values inside of the FIFO. And wherever data needs to cross across the domain boundary, we need to have an explicit domain crossing construct, which tells us, OK, I, as the developer, have thought about this. I know that any latency counting registers that are included in this path, the hardware will deal with them correctly. These are the only places where you actually have to think about the pipelining that is happening in your hardware design. Anywhere else, you should just be able to add registers and it'll work. And here, just to illustrate, within the FIFO, there's actually another latency register because maybe this subtraction and comparison to 4 operation is a bit expensive, so we want to add extra latency register. And then we have another escape hatch called a latency offset, where we can basically say, OK, yes, this wire is at latency x, but I just want to treat it as if it was at latency x plus delta. And this allows us to make these kinds of long latency-bound feedback loops, because otherwise we could never get backwards in time. Right, so to illustrate kind of what these domains generally look like in a big project, I've drawn out all of the domains within the Dedekind project. So they come down like they start from a very small scale, like this internal, what was it called again? It's been a while, but there was like this internal little loop that happened in the Dedekind kernel, and then there was a big block around it, and then that was repeated 30 times, and then data is distributed to these 30 copies, and that whole thing is distributed 10 times, and data is distributed to these copies. And what I want to illustrate with this is that domain boundaries very often occur around FIFOs. FIFOs are very natural places to have these, which is probably also why the boundaries between, say, HLS kernels are often FIFOs. And so here, some FIFOs. The only exception is here, in that innermost block. Instead of a FIFO, we have a dual port memory that we use here. So not only FIFOs can be on the boundaries of these domains. Yeah. Now finally, I'll talk about an example that is known to most of you, the bit serial matrix multiply, because I think this is an example where SUS really shines. So I've worked out this little project in SUS, and I'll walk you through how it works. The bit serial matrix multiply, basically, the goal is you get some compile time matrix that you know, hopefully a sparse one, and then you'll feed the data in bit by bit for each of the input vector elements, because then each of the multiplications that happen within the matrix are only ever operating or are only ever multiplications by 1 or by 0. And this is far, far cheaper to implement than full-size multipliers. So if you're doing a new sus design, you should always start drawing out how you want the data belt to look. So here, I've basically drawn out how the bit serial multiply will work. At the top, we have a bunch of bit shifters, which we get some input we get the input vector, we store them in the bit shifters, and then in the coming 32 cycles, we output them one bit at a time, starting from the most significant bit. These bits are then fed into all of the rows of our matrix. These contain the multipliers by, well, 1 or 0 for each of them. And then the summed multiplications are then fed into our resulting accumulators. The accumulators add them up and shift left once every cycle to accumulate all of the shifted values. And then after 32 cycles, we get our result out. Looking into one of these bit serial rows, we can see we've passed it a vector of specific values, and there are some 0 values in here. And so we want to filter these zeros out first, so that we only actually have to add up the values that were not associated with a multiplication of 0. And so this is roughly what we want to implement. So let's say we get these values, then we just need to add 3 values together, and this is how it should look. So now I'm doing a big sin for presentation. I'm going to be showing a whole bunch of code, starting for the matrix multipliers itself. So this is one of these row blocks. At the top, we get our size and our list of weights as template parameters. We have an interface that is just a combinatorial interface. We start with counting the, OK, I should move that over because now I don't see it. We start by counting all non-zero elements. Right now we have to do that because I don't have like resizable vectors in sus. But once we get features like that, you don't have to do this kind of stuff. We have an edge case. If all of the values are 0, then we just need to output 0. Otherwise, we gather up all of the non-zero elements and conditionally only add them or only retain them in our vector of values to add up if the corresponding bit is 1. And once we have collected all of these values, this is done at compile time, we can use our tree add module again to add them all up and get a result output there. And just as a little side note, this tree add module here, a few slides ago I pipelined it, and they can be of varying pipeline depths depending on how many values there were. And the compiler just handles that smoothly. Like some of these instantiations will take 2 cycles, some of them may take 4 cycles, doesn't matter. Now we've got our accumulators for the bit serial matrix multiply. So again, we take in our width, our height, and our weights matrix. We have some state, which is our cumulative sum. We instantiate all of the row submodules in there. These are the little matrix multipliers. And then we've got, oh yeah, I should have covered that. We have 2 interfaces here. We have a start interface, and we have a feed interface. So every time start is called, it initializes the whole thing. Every time feed is called, it adds this bit together and shifts it to the left. So like this is how you would write that in sus. Then we have our bit shifter. So again, we've got our width, our int bit width. This is just 32 because this is the size of our ints. We've got, again, a start input and a shift input. And then we have a state shift register, which contains the ints that we're trying to shift. When we initialize, we take all of our integer values, we convert them to bit vectors, and then we store them in the shifter. And then on every shift, we shift left. And on every shift, we also push the most significant bit of our shifter. Now here, you have to take care that your state is being maintained well. So start takes priority over shift for assigning the initial values. But then we don't have any priority on start for the actual output because, well, for the last cycle, our state is still maintained when it's being overwritten. I hope I'm not going too fast. That was maybe a bit of a side note. But putting it all together, we have the top-level bit serial matrix multiply module. So we take in all of our parameters, and we just have a really simple combinatorial-looking interface. So we've got a value that says start. We've got our input values and our output values. We instantiate all of our submodules. Then we initialize all of our submodules when start is called. We shift, or we call for every iteration that our iterator generates the shift and feed methods on the submodules. And then we have a latency offset here. And this is more philosophical, because with latency counting, we really want values, or we really want the latency count to reflect the relation between values. And so here, a start value and a values value corresponds to a specific results value. And so we want to have that encoded in the latency count as well. Our module takes 33 cycles to compute through, so we have a latency offset of 33 there to compensate for this, to bring results back in sync with our values. Well, then we'll instantiate it. So here I just generate some random-ish sparse matrix. We instantiate the module, and then I have added an extra wire here called finish, which was just a handy helper for me to have a look at the wave plots to see, okay, at what value should I focus, and at what value is the result supposed to be valid. The reason they're in sync here is because I've explicitly annotated both of them with an absolute latency count, and that means that the compiler will between there add the compensating registers to shift finish over in time to be in sync with result. And so this is kind of the power of latency counting. You don't really need to think about it unless in very specific cases where you do. And then they're just limited. Of course, it's an RTL language, so I have to write my test bench in system Verilog. And so here it is. On the left, you just see the declarations of my wires and my submodule. And on the right, at the top, we generate a 100 megahertz clock. And we basically assign our values. So after 20 nanoseconds, we assign 0 to start to check that the module handles invalid values well. And then a few nanoseconds later, we set up our matrix, we give it a pulse for starting, and then after a while, we finish the simulation. And this is what that wave plot looks like. And so at the top, our clock, start signal, our values, results, and then here's our finish signal that corresponds with one little pixel of the results there. In the middle, you can see the bits being streamed through by the bit shifters. You can see the value at whatever bit the iterator currently is. And then here, we see all of these staggered result sums. And this is because, well, some of the 3 adders took 1 cycle. Some of the 3 adders took 3 cycles. So that's why they're kind of randomly staggered here. An idea I have actually for the simulations there is to compensate for latency counting in the simulation. So to actually shift back all of the signals by the latency count such that you bring all of these related signals back in sync. And for this I'm looking to push the developer of Surfer to implement this, and this might be a really nice addition for the SAS compiler for easy to understand hardware design. Because trying to understand like a fully pipelined design through wave plots, it's insane. Like you lose your mind trying to do that. We can simulate, but we can also synthesize. And so I have this tiny, tiny FPGA from the Xilinx free catalog. And I've had Vivado synthesize the design onto this. And then I went through and I colored the LUTs by the module that they come from. And so you can easily see all of the components in this hardware that we used. We have our 32-cycle iterator in yellow. We've got our state in purple, so this is the accumulator state. We've got our row adders in blue, and then our bit shift in green. And now you may ask, it's a matrix multiply. Why are the row adders so sparse? And my gut feeling is that most of the hardware was actually stolen by state, because Xilinx tends to associate LUTs not like with the module they were from, but with whatever register comes after them. And so the state basically absorbed a whole bunch of the add logic from the tree adder. This is just kind of the way Vivado behaves, and Intel Quartus actually as well. We're nearing the end. I'll just quickly talk about the architecture and future of the compiler. This is what the compiler looks like internally. So we get in our sus files. We first parse them and make an AST using tree-sitter. Then we feed this AST into the flattening process, which basically turns it into a pseudo assembly code. This flattened representation contains all of the wire assignments, declarations, submodules, but it retains templates. And it retains, like, it doesn't execute any of the generative code yet. And this is mostly used for the IDE stuff. Once we actually instantiate modules, then the generative code is executed. We're left with wires, multiplexers, and operators. We can do latency counting on this instantiated module, and we can do any kind of verification we want to do. All of this can produce errors and warnings and diagnostics, which are sent to the LSP server or outputted as CLI diagnostics. And then at the end, the instantiated modules are printed to Verilog, or maybe some other backend in the future, Circuit or Calix. There's a few that might be relevant. I've been keeping this slide for a few presentations I've been doing, because every time I get to cross out a few of the short-term milestones. So right now, there's only 2 short-term milestones left. These are integer bounds. Right now, all of my integers are 32-bit. And, well, no competent hardware design language should really be forcing you to do that. And then also condition pass-through and conditional bindings. This is just for really far nicer syntax to work with. Some vague long-term milestones. So I think a quite reasonable one is to have some kind of formal verification backend. Bool lector has been very interesting to me. I want one that is really quite fast, so it can give you IDE feedback immediately. And it's only really used for basic stuff, like saying the FIFO valid signal should imply the FIFO ready signal, for example. Other things like multi-clock hardware description are also really nice to have and should be there in the near-term future. Inference of template parameters, structs, a built-in simulator, maybe with built-in waveform viewer, maybe different compile targets. And finally, I will leave you with an overly pompous quote. Designing hardware is quite a challenge. It takes the form of terraforming vast landscapes of gates and wires, not only to decide which part does what, but to choreograph an intricate dance between them, one that shatters the moment a single piece steps out of turn. We can, of course, be intimidated by this complexity, pretend it does not exist, and cower behind sweeping abstractions. Or we can choose to embrace it, seek tools to manage it well, and thereby discover new ways to solve old problems. Moreover, in doing so, we gain a profound insight in the work we're doing and carry this insight into our future endeavors. You can now install the SAS compiler and the language server from the command line. There's the repository, and I thank you for your attention.